All right, so hopefully you have attempted it and you didn't just sit there waiting for me to do it, right? You get the most out of this is actually trying to do the derivative before I do, all right? So let's go ahead. I'm going to give myself a little bit more space here. I'm going to move this down a little bit. Let's move that down so I have a little bit more space to work with here. Given the function y is equal to 3 times the 5th root of x to the 4th over 2, find dy dx. Express your answer in radical form without using negative exponents, simplifying all fractions. Okay, so looking at this function right here, right? Some people might right off the bat feel like they need to use the quotient rule, and I would tell you right here to try not to use it when you don't have to. Some of you guys might say, like, but there's a function on top of a function here. That's true, but you could also look at this as a fraction multiplying a function, right? I could try rewriting this thing, and you could always do this. If you can rewrite it into something that makes it easier to take the derivative, that's the first step you should try to do before you actually jump into the derivative. I know some of you guys are like, I know the rules, I have the rules memorized, and I just want to jump into it. And that's all well and dandy, but sometimes it's nice to rewrite your function, right? Rewrite your function. So 3 over 2 could be rewritten as a coefficient, right? 3 over 2 times that, it's the same thing. It's just multiplying in front. And some of you guys have, might not have known this before, but you've probably seen it before. If you have something like y is equal to mx plus b, your slope formula, right? And your slope is a fraction, 3 over 4 times x. You could rewrite that as 3x over 4. These guys are the same, and that's what I'm doing right here. I'm just splitting that up into something that I've done before in the past, right? This is what we're used to seeing our fractions as, if they're just the coefficient, right? If, by the way, if I had like a x in front, then I would just go, I'm sorry, if I had an x in the bottom of this too, then you're right, I would just go ahead and use the quotient rule there, because that x would kind of mess this up. But since there's no variable down there in the bottom, I'm going to just write the coefficient in front, right? And then deal with the function on its own to take the derivative of that on its own. Again, going with the rewriting of this guy, right? I have a power rule in my tool belt, and I need to rewrite this so there is a form of a power to make my life a little bit easier. So I could write this as y is equal to 3 over 2 times x to the 4/5, right? 4/5. And that's all that really needs to be done, so I can go ahead and take the derivative, right? But all I've done, I need you guys to follow along here, right? All I've done is rewrite this, right? Taking the coefficient out, and then rewrite the exponent in power form so that I can take the derivative using the power rule. I can take the derivative of this, and this is actually a little bit easier to take the derivative of, right? This is going to be 3 over 2 times the, for the derivative of this, times the derivative of that function right there. Using the power rule, I just bring down the power, 4 over 5 times x to the 4 over 5 minus 1, which is going to simplify to be negative 1 over 5. I'm going to pause there for a second, double check with you guys. Is that okay? Does it make sense what I've done? Have I lost anyone along the way? Kimberly's saying yes. Monica's saying yes. Thank you for typing that out. Looks good, right? Looks good. Now we simplify the fractions here. So how did it turn into a negative 1 over 5? Very good question. Very good question. So if I have a power, right, x to the n, any power, it could be a whole number or a fraction, and I take the derivative of that with respect to x, d dx, the power comes down in front, multiplies with x, and then what's left behind is the power minus 1. So the power before was 4 over 5. So when I took the derivative of that, I got 4 over 5 in front times x to the 4 over 5, that was the power before, minus 1. And you just have to be able to subtract those fractions. 4 over 5 minus 1. Common denominator is going to be 5 over 5. So I'd write that out as 5 over 5. And then 4 minus 5 is going to give me negative 1. And in the bottom, of course, when you subtract denominators, you just keep the denominator. And that's how I got the negative 1 over 5. Of course, don't hesitate to ask questions whenever you come across one, okay? So simplifying these fractions, the 2 and the 4 is going to cancel out to give me a 2 right there. So I can rewrite this derivative as 6 over 5 times x to the negative 1/5. They want our answer in radical form, meaning they don't want a fraction as their exponent, and they also don't want negative exponents. So I have to simplify that -1/5, right? So I'm going to write this over here. Y prime is going to be equal to 6/5 times x to the 1/5. That negative exponent takes it down to the denominator, right? And to get rid of the fraction on the exponent there, just rewrite it as a radical. So I have here 6/5 times the 5th root of x. And that's my answer. That's it. Pretty strange looking, right? But that's okay. That's perfectly fine. If, by the way, if you were doing a free response question, they don't tell you to simplify all fractions, they don't tell you to write in radical form, I'm okay with you just giving me this as your answer, right? But if they ask for you to simplify, you can do all of that. We don't have to use the product rule. You can use the product rule, Monica. You can use the product rule, but here's the thing, though. This right here is a coefficient, and the coefficient rule would be a lot easier, right? The coefficient rule, I think, is a lot easier. You just multiply by the coefficient. If you do the product rule, where you do the derivative of the first times the second plus the derivative of the second times the first, what's the derivative of a constant? What's the derivative of 3/2, right? It would just be 0. So when you do the product rule, you actually would end up with 0 times the second function, right? Plus the derivative of the second function, which is this guy over here, the 4/5 x to the -1/5, times the first, which is 3/2, which is what we got over here, right? Which is what we got. Okay, so the product rule does work, right? But since that first function is just a constant, it'll just go to 0 anyways, and you just end up with what we end up with over there, right? Hopefully that makes sense. So it is true. It is something times something, but the first function is a coefficient. If we face another problem like this, how do we know which rule to use? That's the part that is part of calculus. As long as you apply the rules correctly, you should end up with the right answer no matter what. If you had done this using the quotient rule, you'll still get the same answer. You just did a little bit more work. And there's nothing wrong with that. You'll never get marked off because you used the wrong rule. It's as long as you end up doing it correctly and you get to the right part at the end. Okay? So don't stress out about which rules you should use. It is a technique that you will develop and you will learn just the more derivatives you do. You'll realize, like, man, this was actually a lot of work to do. And then when you do it enough times, you're going to realize, like, or you hopefully have done start realizing it when you start doing the homework, that sometimes there might be an easier way. And there's no way for me to tell you, like, this way is always going to work for this one, this way is always going to work for that one, because there's infinitely many ways to combine functions. And I can't give you all the possible combinations, right? The easiest way is just for you to get practice on there. And you kind of develop an instinct of, like, I think this way will be easier than the other way. And that's all I can really share with you. Like, for example, if you look at number 2, right? I can't rewrite this as a coefficient, right? I can't rewrite the 1 minus 4 with a 1 as a coefficient and then divide the x into x cubes. That's just mathematically impossible. I can't go in there and, like, you know what? I'm just going to cancel that x and that x to make that x squared. That doesn't work algebraically, right? So I can't do anything clever for this one. So since I'm looking at number 2 right now, I kind of just have to go in there and take it for what it is. And this one I do have to use the quotient rule for, right? I can't do anything. I can't simplify it. I can't write it any other way. Actually, that's not true. That's not true. You could, if you wanted to. If you wanted to, don't write this down. If you wanted to, you could rewrite this function as x times 1 minus 4 x to the third to the -1 power. You could, I guess, rewrite it like this, right? If you wanted to. And then use the product rule here. You can say this is the first function and this is the second function, but we haven't actually quite learned how to do that yet for something like this, right? Where you have a function outside of a function. So that might not work too well right now. But you could do that if you knew how to take the derivative of that. But since we don't, and I can't move it around, then I just go ahead and apply the quotient rule for this one. And I hope that answered your question. I know it seemed like a non-answer, Kimberly, but it's basically that's the only way that we can apply and attack these problems is basically you don't actually you're going to develop your ways of doing it. I just can't give you all the possible combinations because sometimes they'll look like this. Sometimes for the first problem, it'll look like this. Sometimes it'll look like, oh, 3 to the 5th root of x to the 4th over cosine of x. And I can't do the same trick that I did here with the power rule for this one, right? You can't do that with that. You can just go ahead and just use the quotient rule for that, for it to work, okay? All right, let's go ahead and take a look at the second problem here, which is going to be a product rule problem. I'm sorry, quotient rule problem. So let's go ahead and take the derivative of this guy. This is my high function. This is my low function. And we're going to go ahead and do the low d high minus high d low over low low. All right, so we got the low function, 1 minus 4x cubed. D high, derivative of x, is just 1 minus high x times the derivative of the low, which is going to be, looks like the derivative of 1 is just 0. Derivative of negative 4x cubed is going to give me negative 12x squared, I believe. I do believe, right? And this, of course, is all over low low, which is 1 minus 4x cubed squared. 1 over 4x cubed squared, right? The whole thing in the low getting squared, right? So f prime of x, we're going to go ahead and take the derivative of this guy, simplify this out because they're asking us to do it in the most simplified form. So I have here 1 minus 4x cubed. Negative x times negative 12x squared is going to give me a positive 12x squared all over 1 minus 4x cubed squared. If you want to, that's as simplified I think is going to get. If you want to, you could rewrite this in descending order. Negative 4x cubed plus 12x squared plus 1 all over 1 minus 4x cubed squared. I think that's all you can do on this one. I can't factor that numerator. Did I distribute everything correctly? Wouldn't it be 12x cubed? You're right. Oh, you're right. That should be 12x cubed. Good catch. Good catch. Yeah, so I can change that top. Oh, you guys are paying attention. All right, so we get here 12x cubed minus 4x, which is going to give me 8x cubed. Oh, you guys actually saw it. I'm so happy. 8x cubed. Did I do any other mistakes anywhere else? I'm a little paranoid now. Is everything else okay? I hope that's okay. Plus 1. Aha. All right. No, you're good? All right, sweet. And then I think that is the simplified version. Yeah, I think that is. This is a difference of, this is a sum of cubes. You could factor that out, but I'm not going to bother factoring it out because I don't think that's going to match up with what I have in the denominator to cancel out. If you guys do remember the sum of cubes, this looks like it's 2 cubed times x cubed. So you could say it's 2x plus 1 cubed. So this would factor out to 2x plus 1 times 2x. So opposite. 2x. No. 4x squared minus 2x plus 1. That's what that would factor to. I wouldn't even bother factoring it because nothing cancels out with this guy right here. Actually, that's a lie. This would be a difference of cubes, but squared. I'm not even going to bother factoring it. I think this is as simplified as it's going to get because if you factor out that bottom one, I don't think it cancels out with anything. I don't think it cancels out with anything. This would be 1 minus. No. 4 is not a cube. 4 is not a cube. Now, there's nothing else we can do with that. And yeah, that's okay. We can try and look at it. And we looked at it and we saw there's nothing else there. So that's pretty much what it's going to end up at, right? 8x cubed plus 1 over 1 minus 4x cubed quantity squared. Do you ever need to factor out the denominator? Yeah, sometimes, Emily. Sometimes. But most of the times, though, you don't really need to. You leave it in this form most of the times and just hope that the numerator will factor out and cancel out with the denominator. Most of the times, though, you don't bother. You don't really need to multiply this whole thing out. Like it doesn't really help the problem most of the times. How do you know what to do most of the times? Again, I can't give you every possible scenario or every possible combination where that's going to be the case. But rule of thumb, most of the times when you're simplifying fractions, you simplify the top, and the denominator, you try to hope that it is already factored out, and you kind of leave it alone, right? You kind of leave it alone, especially with the quotient rule. It's already two things multiplying with each other. I wouldn't bother multiplying it out. Even if it looks like it's a simple thing to FOIL out, I wouldn't bother. I wouldn't bother with that. Okay. All right. Hopefully that answers your questions. All right. That's practicing derivatives. You always should be practicing that. I should give you guys some more problems soon. I think I have another worksheet for you guys to try on that, so you can practice your product rule, your quotient rule, your coefficient rules, your power rules, and your constant rules, right? And your addition and subtraction rules, right? You should be practicing those along the way. Hopefully you've done the homework and you've seen them. And then also now you've learned a couple of trig functions as well, right? All right, that's enough of that. Let's see here. Last time we talked about understanding if a function is differentiable or not at a specific point, right? At a specific point. So if I was looking at, let's say, a graph of this guy, and let's go ahead and take a look at a graph of that guy. Give me a second here. Let's open up my favorite graphing app here. And we were starting off with, let's see here, 3 times the 5th root, which, by the way, if you ever don't know how to type in like the higher power roots, there's a button over here that has functions, right? And you can go into miscellaneous, and there's the nth root right there. So if you ever need to type in like a 6th root or a 5th root, you just click on that, and it'll have the cursor there automatically. So you can type that this is going to be the 5th root of x to the 4th, right? This whole thing, of course, is being divided by 2. Boom. Right? And when you look at this guy, right, it looks like a nice graph, right? And even then, we were able to take the derivative of this thing, and we got this guy right here. But this is where you got to come in and start also looking at the domain and mostly the domain of the derivative, right? If you look at this guy, is there a number that I would be messing up this fraction if I were to plug into x right here in this derivative? Do you guys see a number that would mess this up in the derivative right here? Y prime is equal to 6 over 5 times the 5th root of x. What's a number that would mess up this function right here? What's something that would screw up this thing if I plugged into x? Would there be anything there that would give me an undefined value? I? A negative? No. Close, because you're thinking of a square root, right? If you put a negative into a square root, you're right, you would get an I. But this is a 5th root. It's an odd root. It's an odd root. 0, Juliet. David, yes, 0. What happens when you plug in a 0 into the derivative? If I was evaluating the derivative at 0, I would get 6 over 5 times the 5th root of 0, which is just 0. 6 over 0 is undefined, isn't it? That means that the derivative does not exist at 0, right? The derivative does not exist at 0. And you can see that, right, numerically, just by looking at the function and just plugging in that number, right? But here's the neat thing, though. If you were looking at this graphically, right, can you guys see graphically that at 0, the derivative doesn't exist there, even though the point exists there? This function is continuous, isn't it? It's continuous, all right. The limit as I approach from the left-hand side is equal to the limit as I approach from the right-hand side. The function exists there. The limit exists there of that function. But the slope of the tangent line does not exist there. The tangent line does not exist there, right? Why is that? Why is that? Why does the slope of the tangent line not exist there? What do we call this point? It's a cusp. Very good. And Monica, very good with the second term that I was looking for. There's no local linearity, right? There's no local linearity. If you zoom into any spot and you want to see if it's differentiable or not, it should turn into a line, right? Into a straight line. That's what local linearity is, right? But this cusp, very good use of the word there, Ryan, this cusp has no local linearity. The more you zoom in, the more it turns into a V shape. You see that? And you're like, knock me, it almost turns into a vertical line. That's not helping, is it? In fact, it doesn't ever actually become a perfect line. It just becomes a very, very narrow V. So there's no local linearity here. By the way, if you guys haven't done so already, I really suggest you open up Desmos at some point in this class. Not this class particularly, but just in general during this semester, and just play with functions. I don't know if you know this or not, but if you have a mouse and you use the mouse wheel, you can zoom in and zoom out with the mouse wheel, and it's just kind of fun to do if you want to look at a function that is differentiable or not. Okay. The other function that we did this morning was x over 1 minus 4x cubed. 1 minus 4x cubed, right? And we got something like this, right? Oof, right? Now, this thing is pretty much differentiable everywhere, including here, right? There's no cusp here. There's no corner right here. So there's probably, if I zoom in right here, right, it looks like it was going to form something, but if I zoom in enough, look at my line. What happened to it? It becomes, well, look at my curve. It becomes a line, right? It has local linearity there. So that means it is differentiable at that point, right? It is differentiable there. It is a weird looking curve, right? Including here, that's also a weird looking curve. But if I zoom in enough, right, forms a straight line, does have local linearity. But there is a point that is not differentiable on this curve. There is a point that's not differentiable on this curve. And it's going to be right here where the function is discontinuous, right? So that's another property where you can say that the function is not differentiable. It's not differentiable if it's not continuous there, right? That's another thing. So it's not continuous right here. I don't know what that value is. The x value looks like it's approaching 0.65. You could calculate it algebraically, of course, if you look at the derivative right here. It's going to have a problem at, well, it's going to have the same problem right here at whatever number is going to make that 0. Whatever number that's going to make that 0. I think it's like the cube root of 1 over 4 if you solve that out, right? Whenever 1 minus 4x cubed is equal to 0, this is when you're going to have a discontinuity. And if it's a discontinuity, that means that you cannot take the derivative of that. It is not differentiable at whatever that point is going to be. And I think you have to just do some algebra. You solve it, you know, just like you've done in the past, where you solve where the vertical asymptote is. That's where all this stuff is connecting, and I hope you guys are making that connection as we go through this stuff. Okay. All right. So that's hopefully you feel a little bit better with all this stuff, right? I know we spent a lot of time on this warm up, but that's okay, right? That's okay, right? Hopefully it makes you feel a little bit more comfortable with all of these things. All right, today, if you want the title for today's notes, we are starting 2.5, velocity and other rates. Velocity and other rates. If you guys want a second to copy that down, velocity and other rates, right? You guys know what velocity is, right? You guys have heard of that. All right, we did a little bit of talking about velocity in this class, right? And then also, if you're taking physics, you're probably very comfortable with velocity at this point, or if you've taken physics, you're very comfortable with it, I should say. If you're taking it right now, maybe you started velocity in position and acceleration. I'm not too sure. You should be there, I think. I'm not sure, but if not, we'll talk about it right now. So if you guys didn't get that, let me copy that, and I'll put it down here so you guys can copy down the title if you want to copy down the title. So 2.5, velocity and other rates. Before I actually start talking about velocity and other rates, right, we need to talk about position first of all, okay? Position is basically where something is located at a specific time. So when you deal with position, we traditionally deal with two variables, right? The independent variable, it will be time most of the time. And the other variable is the actual location or the output value, right? The dependent variable. We denote that with either a x or a y, or traditionally in physics, they use s for position, right? This is a position function, right, with respect to time. Position function, right, using time, right? Position function using time. So for example, if I were to graph this out, right, the x-axis would actually be labeled with a t. The y-axis would be labeled with a s of t. And if I had something like this, right, that looks something like that. Let's do it a little bit better. Let's say he went like that, stayed somewhere, and then came back home, right? This initial dot is their starting point. It's where they were at the beginning at time is equal to 0, right? This is where they started. And then let's say, let's say this is in hours. No, that's too much. Let's say what this is in minutes, and this is after t is equal to 30 minutes, right? This person went somewhere, they hung around there for a little bit, and then they came back after 30 minutes, right? That's what this function represents, right? S of t is the position where they are at a specific time, right? So nothing new, nothing fancy, right? So you can see like this is, if this is one, I don't know what these values are. That should be like 15. This one should be like 7. So this right here would be their position at 7 minutes, right? And then this could be their position at 0 minutes, okay? Nothing too crazy, nothing too fancy, right? And with that, right, let's say the position is, by the way, in feet then, and this one's in minutes, right? So given that this is a position function, right, and again, this is hopefully nothing too new, nothing too fancy, nothing too crazy for you to see, you can calculate the average velocity, right, the average rate of change, right? How much does he change in position compared to the change in the time, right? And we can do that by calculating, what's their time initially, right? Or what's their position initially? Oh my God, knock me, get it together. What's their position initially, right? And then subtract that from their position after their final time. Where are they after a second time t, right? And we could do the same thing here by comparing their times and subtracting them from each other. So t final minus t initial is how that's usually set in physics. In calculus, we just denote them with zeros and ones, right, to denote like one point from another point, right? So for example, here we can say like, the average rate of change, we could say from this point to this point would be s of 7 minus s of 0 over 7 minus 0, right? And this, of course, will tell us the average, right, rate of change. And this is nothing new. We've seen this before, right? And that's where this comes from, right? Now, average rate of change, of course, is basically, in this case, though, when we're dealing with position, we call this the average velocity. And that's all velocity is. It's the change in position over the change in time, right? And what makes this the average is we're just looking at the endpoints, right? We're just looking at the endpoints from here to here, okay? Now, this is going to get a little weird, and if it doesn't make sense, just hang on tight and follow along. I promise you it will make sense in a second here. You can break this down. This second time, right, is initially just whatever your time was to start with plus some random value of h. You're like, oh, knock me, here you go with the h again. This is just a placeholder. It's like you're adding this random number here to go from this time to t of equaling to 7, right? So I can say that this is the same thing as t plus h minus s of t, right, over t plus h minus t. But again, of course, that right there, this t and this minus t would cancel out, right? And I would have here, this rate of change would be s of t plus h minus s of t over h. And we use this to help us find the velocity, right? This helps us find the average velocity, right? This helps us find the average velocity. I wouldn't suggest you write that down, though, right? Average velocity would be easiest if you just keep it in this form. But why did I write it like this? Well, if we include this new variable h, right? If we include this new variable h, and then I took the limit as h approaches 0 of this said function, this now tells us, right? This now tells us the derivative of the position function, doesn't it? It tells us the derivative of the position function. But not only that, we know that the rate of change of position is this thing called velocity, right? And if I'm looking at the derivative of this guy as this thing approaches 0, right? This isn't going to tell us the average velocity anymore. This is going to tell us the oh my God, knock me. This is going to tell me the instantaneous. That's not spelled right, is it? That's an E. That's supposed to be an E. Instantaneous. I hope that's spelled right. Instantaneous velocity. Instantaneous velocity, which means that we know the velocity at that specific point, at whatever point t we want, right? We don't have to do the average anymore. If I wanted to know how fast was this person traveling exactly at t equals to 7, I can do this derivative, right? The derivative of the position function will give us the instantaneous velocity at that specific point. Whereas if I use algebra 1, I can find the average velocity if I'm given 2 points, right? And kind of work my way there. So if I wanted to get something that's kind of close to this, using the algebra technique, I would just pick a point that's really close, like s of 6, for example, and then do the slope formula with s of 6 and s of 7 divided by 6 minus 7, right, to give me that. Whereas if I want the instantaneous velocity, now I know using calculus, I can take the limit of this slope formula, right, and I can calculate that out. I spelled it wrong? Oh my gosh, I forgot so many letters in there. Instantaneous. Man, that just doesn't look right, but okay. Instantaneous. There's 2 tanes in there? Oh yeah, instant. Yeah, that makes sense. This is why I'm your math teacher, not your English teacher, right? No, that's not a good excuse. I should know how to spell these words. Instantaneous velocity. That looks wrong, but I believe you guys, and that is right. Anyways, I get distracted very easily there. So yeah, so using calculus, right, we can find the instantaneous velocity now, but we also know, thanks to chapter 2, right, we don't need to evaluate this limit this way. If we can identify that this is what that is, I can just take the derivative using rules that I've learned in Unit 2, like the power rule, the addition rule, right? I can take the derivative using those rules instead of doing this limit definition. But that's all I'm trying to say here is that when I'm calculating this s prime of t, or the derivative of position, what I'm essentially calculating is the velocity. That's all it is. It's just the velocity at a specific point, okay? At a specific point. So let's go ahead and take a look at a problem real quick here. I'm going to cheat and copy this instead of retyping everything out. You guys are going to be angry because you'll have to write this all down by yourselves, or you can screenshot it in the Pear Deck slide. So this is the problem we're going to be working on right here. Boop. Come on, buddy. Like, mouse, do you really want to just hello? There we go. And the function is going to be not s is equal to 160t minus 16t. It's going to be minus 16t squared. I'm going to switch the Pear Deck over, so if you guys want to just screenshot that for yourself, or if you want to write it down by hand, you can as well. I'll leave that choice up to you. But I'm going to switch the Pear Deck over right now. Right? And we're going to work on this one piece at a time, right? The first question up is, what is the position of the rock at t is equal to 0 and at t is equal to 2, right? So this is right here. This is the position function. I know it just says s, but it's technically s of t because the variable we're dealing with is t, right? So check this out. So what's the position of the rock at t is equal to 0? Right, I'm going to do that one, and then I want you guys to try the one for 2. Right, so at t equals 0, all I'm saying is go to the s function and plug in 0 wherever you see time. Right, so this would be equal to 160 times 0 minus 16 times 0 squared. And this is going to be equal to, what do you guys think? This times 0 is 0, that times 0 is 0 as well. So the position of this heavy rock at t equals to 0 is 0 feet, right? Meaning at t equals to 0, this thing has not launched off the ground yet. It's still at t equals 0. It's still there. Okay. So if you guys could, can you guys, on the pair deck is open right now. Can you guys find, right, t equals 2 for me? Can you find out what the position of the rock is after 2 seconds? Can you guys go ahead and do that real quick? Put it into the pair deck for me. If you guys have lost the pair deck because you lost connection and you just rejoined, let me undo and let me go ahead and find the link for the pair deck again, and I'll put that back in the chat for you guys right there so you guys can do it. There we go. So there's a good 30 of you guys out of the 36 that are in this classroom. So there's 6 of you guys who are not in this pair deck still. Please get in there. You can just write your answer if you want. You could also show the work if you want. All I ask though is please don't forget the units when you're doing this problem. Please don't forget the units. So a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s, which is equal to 160t minus 16t squared. All right. So it looks like a couple of you guys already have an answer here. Jocelyn, very good, very good. Kimberly's working it out. Max, good job. Ava, interesting answer, interesting answer. Kaylee, nice, nice. Eric, nice. Juliet, good. Oscar, all right. I double checked that number though, Oscar. Good job, Jeffrey. Good job, Calvin. Good job, Joe. Brian, nice. Fatima's writing it out. I like it. David, I would double check that. I would double check that. Monica, same thing. You might want to double check that. Diana, good. Brian, nice. And then I'm still not having answers from 11 of you guys. I scratched that. 9 of you guys. 10. Plus 6, I guess. There's still 6 of you who aren't. Oh, I lied. Now we're at 31 students. We're at 31 students. Nice. So I'm still missing 5 of you guys in there. But that's okay. I'm feeling shy. I don't know. Maybe, maybe not. But take a look here. Right? If you don't know what to do yet, right, this is the function we're working with. It's the position function, right? And the reason why it's S is because I think it has to do with Latin for position, if I remember correctly. You can try looking that up, but that's what the always thing that I always found weird. If you do take physics, the functions they write out for acceleration, it's a of t, because a for acceleration. For velocity, it's v of t, right? For position, they don't use p of t. I don't know why. They use s of t, and I believe though it's because of Newton. When they first wrote it out for position, I think the Latin word for position starts with an s in Latin, so they would write it out as s of t, I believe. Anyways, talking too much. The function is 160, right, times 2, right? That's all it is. That's all that represents. T is equal to 2. You're going to the function. You're evaluating at 2, right? So how far has this rock traveled after 2? I'm not saying how far it's traveled. What is its position after 2 seconds? All right, that's actually different from how far it's traveled. That question is another question in itself. But right now, right, what is its position after 2 seconds? So let's go ahead and take a look here. So this is going to be 160 times 2 minus 16 times 2 squared, right? I think you got to be careful with this one, right? This is 2 squared, not 16 times 2 first and then squared. Make sure you do order of operations when you calculate this out. And you should get s of 2. And most of you guys did get this. And I'm looking at your answers right now. Most of you guys did have this. This is 256 feet. 256 feet. What's the position of the rock after 2 seconds? It is now 256 feet in the air. That's terrifying, but that's what it is, right? That's all it is. Okay? You guys okay with that? Is that all right? You feel okay? Yeah? Yeah? It's not bad, right? That's not calculus either, but that's not bad, right? It's just a position function, right? Okay, let's keep going then. I'm gonna switch your pair deck over. Or actually, not right now, but I will switch in a second. The next thing we want to talk about is the average velocity, right? And when you're talking about the average velocity, right, you're just looking at the endpoints, right? You're just looking at the endpoints that you're dealing with here. So the function is this function right here, but if I'm looking for the average velocity, right, the average velocity, whenever they say average, you just look at the slope using the endpoints there, right? So the average velocity, I'd say, is going to be equal to, you ready? S of 2 minus S of 0 over 2 minus 0, right? That's what makes it the average. It's the average slope. It's the average rate of change, right? And that's just the slope formula for those two endpoints. And the two endpoints is going to be 0 comma whatever S of 0 is, which is going to be 0 because we just calculated that. And then the other point that we're comparing it to is 2 comma 256, right? Those are the coordinates we just found up here. And to give us the average velocity, it's just the average rate of change. And it's just those positions, right? So we have here 256 minus 0 over 2 minus 0, which is going to give me 256 divided by 2, which is going to give me 128. The 8. Wow, that was 128. And here's the thing, though. The units actually do matter here now, right? The velocity, some of you guys just know by heart, velocity is going to be a distance divided by a time, right? A distance divided by a time. But how do I know that this is seconds? T, oh, shoot, I didn't actually put that down in there. T is actually in seconds as well. I should have explained that. So this is 0 seconds. This is 2 seconds instead of me saying minutes or whatever, not giving you the units at all. But here's the idea. In the top, it's 256 minus 0 feet, right? So 256 feet. In the bottom, it's 2 seconds minus 0 seconds. So you end up with this unit of feet in the top and seconds in the bottom, which I'm hoping now makes sense when you are dealing with speed or velocity, right? It kind of makes sense. Miles per hour is the idea that you traveled a certain number of miles per hour. Feet per second is the idea that this thing has traveled 128 feet every second. That's the average speed that this thing is going at, right? That's the average speed. That's not the actual speed when it first launched, though, is it? When it first launched, the actual speed was 160 feet per second. But of course, as it's traveling through the skies, the velocity is changing, right? The velocity is changing. It's slowing down, because if it didn't change, that thing would just go off forever towards space, right? But since the velocity is changing along the way, right, the average right here is a little bit lower, okay? And that's how you calculate the average velocity. It's just you're looking at the endpoints and you just calculate the average slope, right? The average rate of change from one point to the other. Now, when it asks, what is the velocity at t equals 2? What is the velocity at t equals 2? That is the instantaneous velocity now. We're looking for v of t. And of course, if you're looking at it, the instantaneous velocity of it, this is technically the limit, right? As h approaches 0 of the position function, right? Of the position function of t plus h minus s of t all over h. But I'm not going to do all this. I already know that this right here, this thing right here, thanks to our quiz the other day and thanks to our practice of looking at derivatives over and over again, this is just telling me to look at the function s of t and take the derivative of it. That's all the velocity function is. It's the position function with taking the derivative of that function, right? And you'll say, well, okay, what does that mean then? Well, the position function, s of t, is equal to this guy, 160t minus 16t squared. If I'm looking for the velocity, right, that just means to take the derivative of my position function. And thanks to my rules that I've learned in this chapter, I don't need to use this thing anymore. I can see that that's the connection now. But instead, I'm just going to go ahead and use my power rule, my coefficient rule, and my addition or subtraction rule of derivatives. So what's the derivative of 160t? The derivative of 160t is just 160. minus the second function over here, which is going to be 16 times t squared. The derivative of 16 times t squared is going to be 32t. So this right here represents the velocity function, right? The velocity at any specific point, because it's the derivative of the position function, right? And I promise you, if you went through and did the limit definition of it, this is what you would get. And I'm hoping you understand that's helping us to find the slope exactly at one's particular point, the slope of that said tangent line, right? The slope of a line that's touching at one point exactly, and that's the tangent line. And that's all this velocity is. It's just the slope of the tangent line at any specific point t, right? So when this question is asking what's the velocity at t is equal to 2, I simply just plug into this function right here. So I would go v of 2 is equal to 160, right? Wait, hold on a second. Yeah, that should be fine. I can't see my Pear Deck stuff, but yeah. So 160 minus 32 times 2, okay? And then, so my velocity exactly at 2 is going to equal to 160 minus 64, I believe, which is going to give me, what is that real quick? What do you guys get? 160 minus 64, what is that? 90, 104, 96? Is it 96? 96, yes? Okay, Max, you're double checking with me. 96, and of course, remember the units for this. This is 96 feet per second. Feet per second. And that's my answer, right? 96 feet per second. So hoping that makes sense for you guys. If you take a look at this thing, right? The average velocity, right, from 0 to 2 is 128 feet per second, right? It was this steep line right here, right? But if you look at the velocity exactly at 2, it has a slope of 96 feet per second. It's not going as fast anymore. That's because of gravity, right? It's not traveling as fast as it gets to the peak of this parabola. But let's go ahead and take a look at this real quick. Hold on a second. Yeah, shoot. I was supposed to give you guys the Pear Deck slide for this, but it's okay. I did it already for you guys, and you can do this in your notes. You don't have to do it on the Pear Deck. But let me show you this real quick, right, on Desmos. I just wanted to share this with you. The function is, let's call this f of x, right? I know it's s of t, but it's okay. I'm going to switch it out with this f of x function right here. It's going to be 160x minus 16x squared, which looks like this. Whoa. This looks like this parabola right here, and it looks like it goes from 0 to 10, and it goes all the way up to, what's that number up there? All right, let me adjust this window real quick. And this is going to go from, let's say, negative 10, 450. There we go. So here's my window, right? Here is the function, the position function graphed, right? So if you guys can imagine, right, the rock, this rock, not the rock, this rock, right, at t equals 0 is on the ground, right? And then it gets a massive explosion and it gets launched into the air, right? So as time goes on, this rock is going up here, and then at about 5 seconds, it reaches the top. Yeah, not Dwayne the Rock Johnson, just a rock, right? This rock, right? A heavy rock gets blown up, and after 5 seconds, it reaches the top, and then after 10 seconds, it comes back down to the ground, right? So this is a rock that's traveling up into the sky over a specific amount of time, and then it travels down, right? And this is over 10 seconds, right? So what we've essentially done, though, is realize that you can graph, you can also take a look at its velocity, right? You can also take a look at its velocity. And that's what I want to show you right here. When we calculate the average rate of change, right, we have here is going to be y. All right, let's see here. I'm going to do a little bit of All right, well, why not? Y minus, shoot, y minus 0 equals to the slope, which is going to be, give me a second here. Don't write this down, but you can see my thought process of this. Here over 2 minus 0 times x. Okay, and this is of course going from 0 less than x less than 2. So there we go. So here is the purple line right here. I don't know if you guys can see it, but this purple line right here, right, from here to here, has a slope, right? And that slope is equal to f of 2 minus f of 0 over 2 minus 0, which is a 128. That's the slope of this purple line right here. That's the average rate of change. That's the average speed, the average velocity, not the average speed, the average velocity from start, from t equals 0 to t equals to 2, right? Julia, are you doodling in the notes? Distracting me. Anyways, that's what we essentially did for calculating the average velocity, right? We calculated the slope of this purple line. You see that? We calculated the slope of this purple line. And then what we did to calculate the actual velocity itself is we calculated the slope of the line that's tangent exactly at 2, right? And what that looks like is this right here. Let's say, man, I used to be so much better at this. Y minus f of 2, right, is equal to f prime of 2 times x minus f x minus 2. There we go. So there's the red line right there. Hopefully you guys can see that. Let's make that so it's not going all the way over there. So let's go from like 1 is less than x less than 3, for example. And there's the tangent line. Can you guys see that okay? Right? So, and the derivative evaluated at that point is, let's say, 96. So you guys can see, hopefully, right? Oh man, that's so hard to see. But there's the red line. That's the tangent line, right? That's the tangent line. And that tangent line is the exact velocity at that exact point, right? That's what we found out. We found out the velocity at x equals 2, right? That's the instantaneous velocity. That's what we're doing here. That's the connection I hope you guys can see, that if you have position, the derivative of position is velocity. And when you plug in the values, you can actually find out the instantaneous velocity at any point time t. Whereas if you did it back when you were back in algebra, or IM1, IM2, IM3, you always calculated the average. You always calculated between 2 points, right? So you need to be able to identify between the two now. You will be asked to calculate the average velocity still, but now they're asking what is the exact velocity at an exact point, okay? Anyways, let's take a look at another problem, right? And let's have you guys try this one out, okay? Let's see how we do this one over here. So I'm going to go ahead and change the pair deck to the next one, and I'm going to double check that this is the right one. Let me take a look here. Yes, that is the right one. Can you guys try this one out, right? Try this one out. Find the velocity and find the acceleration. Just do the velocity part first. Find the velocity first. So I'm going to go ahead and put that onto this screen as well so we can have it. And there we go. This is the one we're looking at. Copy. If you guys can't see the pair deck, I'm going to put it right here. This is what I was asking from you guys. So start off with the first part. Can you guys find the velocity? Find the velocity when t is equal to 3 seconds and when t is equal to 6 seconds. So find the velocity and then find it when it's t is equal to 3 and when t is equal to 6. And then go ahead and type that into the pair deck for me. Where's my mouse? There you are. Type that into the pair deck for me so I can see that you guys are getting how to do this. Right? I'm not asking for the average velocity, right? I'm not asking for the average velocity. I'm asking for the velocity exactly at 3 seconds and exactly at 6 seconds. So what's the velocity at 3? And what's the velocity at 6? Now, of course, in order to do that, you need to find the velocity function first, which I think you guys can. So go ahead and do that real quick. What is the velocity? Oh, shoot. It's a t squared, isn't it? Is it t squared on your notes? Is it t squared on the pear deck? 16t squared? Is that what it says? Yes, it does. Mine doesn't say it, but there. Oh, it should be 16t squared. Yes. Okay. Ooh. So if you guys could go in there, find the velocity function, right? Find the velocity function first. Which, if you're lost and you don't know where we are, if I have a position function, in this case, the position function is the h function. I'm assuming for height, right? But we can also use s, right? The derivative of this position function or the height function, whatever it is, if you take the derivative of it, it's going to give you the velocity. It's going to give you the velocity. So take the derivative of that function. What do you get? And then, with that function, find out what the velocity is at exactly 3 seconds and at exactly 6 seconds. What is the velocity? All right, I'm gonna take a look at some of your answers right now. Oh, only 6 of you guys have responded, but that's not bad. All right. Looking good. If you're still working on it or you don't know where to go, right? Start with finding the velocity function. Right? The velocity function is just the derivative of your position function, right? So take the derivative of this, and this is what you should get. Derivative of 3 is 0. Derivative of 135t is going to be 135 because we're taking the derivative with respect to time, of course, minus 16t squared. The 2 comes down. It'll be 16 times 2, which is 32. T to the first power. T to the first power, right? Because we subtract 1 from it using the power rule. There's my velocity function. That's it, right? If you're asked to find the velocity of something, and it doesn't say average velocity, it just says velocity, take the derivative of it, right? Take the derivative of it. If it asks you to find the average velocity, they always put one or the other. Can I put the negative 32t in front? Of course, Max, you can. Please make sure, though, you include the plus 135 at the end. Make sure you have the sign there, or else it looks weird if you don't have the sign for the 135, I should say. But yeah, Max, if you want to write it like that, you can. That's perfectly fine. So v of 3 is simply asking us to take the velocity function we just found and plugging in 3. So it'll be 135 minus 32 times 3. And I'm going to cheat and look at some of your answers and see what you guys get. David, I'm going with your answer. So if you're wrong, everybody blame David. Aurelie, we are not doing t of 6 minus t of 3 or vice versa, right, Aurelie? Because if you are subtracting those two, that's when you're actually calculating the average between 3 seconds and 6 seconds. They want you to find the velocity when t is exactly equal to 3 and when t is exactly equal to 6. So I'm only going to do it right here. I'm not going to subtract these guys. I'm just going to go ahead and tell you right now. The velocity at t is equal to 3 seconds, that's just your answer right there. So we plug this in, right, and you get 39 feet per second. Because I'm not asking for the average velocity. I'm just asking for the velocity right there. So I take it and I plug it into the derivative. And again, if that's not the right answer, everyone yell at David. All right, let's keep going here. For velocity at 6 seconds, right? It's the same thing. You have your derivative function, which is this guy right here, 135 minus 32t. Right, so it's 135 minus 32t, but instead of t, you get to plug in 6. Right, you get to plug in 6. Monica's saying you got the same thing. All right, we don't have to yell at David. Wait, so you find the derivative and then you plug in 3 and 6? Yeah. I'm not doing 6 minus 3 or 3 minus 6 because I'm not finding the average velocity, right? I'm finding the velocity, the instantaneous velocity, Kimberly. So I don't need to do the s of 6 minus s of 3 over 6 minus 3, which, by the way, Aurelia, if you were doing that and you were looking for the average, it wouldn't matter what order you put them in as long as they were consistent, right? That's how you calculate slope. It doesn't matter what order you put them in. It'll give you the same answer as long as you're consistent with x2 minus x1 with your y2 minus y1. Anyways, for the velocity at 6 seconds, David got negative 57 feet per second. I'm going to trust you on that as well. And is it okay for my velocity to be negative? Is it okay for my velocity to be negative? Is it okay for my tangent line to be negative? Is that all right? Is that okay? Can that be okay? Can that be all right? Yes, Sam, yes, you actually can. And all that means is the tangent line is negative, right? That means that the tangent line is negative. And that's okay. Of course, that makes sense because it's falling, right? So velocity is going to be negative because it's now tumbling down towards the Earth, right? This is a very weird graph, by the way. But yeah, when you look at this thing, right, you can kind of see, right? You can kind of see this, this tangent line. I'm going to change this up just a little bit here. Let's go ahead and change U to an A. I'm going to change U to an A as well. And I'm going to change U to an A as well. And let's make this A minus 1. And this one will be A plus 1. And this will be, let's modify U going from 0 to 10, increments of 0.5. That work out? So I don't know if you guys can see that. Right? So if you look at the velocity function, this red line right here, right? When I was looking at it at exactly 2, the red line had a slope of 96, right? The slope of this tangent line, right, exactly at 2 was equal to 96, right? And this is the last example. But if I follow this tangent line as I move along this graph, right, you see how the slope at specific points start to change, right? So it's positive over here. In fact, at the very start of it is very positive. It's like super positive, right? In fact, at the very start, it's like at 160, right? And then as I keep moving along, the velocity gets slower and slower, but that's because the acceleration of gravity is slowing it down, right? And then it gets to this part right here at the peak, and you notice the slope of that tangent line is now 0. And if I start going to the other side, right, I have a negative slope now, and it's starting to travel down, right? The function is decreasing, the original function is decreasing, but the velocity is now negative. The velocity is now negative. So I have over here, right, positive values for my velocity, 0, and then a negative value for my velocity. Okay? And that's all that's happening. And that's happening in this one as well, because this one's not a rock. This is apparently is a student that's falling off a cliff. It's terrible. But yeah, so he's falling. So initially when he was falling off this cliff, he initially was going upwards. He must have jumped, and he must have jumped pretty well because after 3 seconds, he's still traveling up, right? After 3 seconds. What the heck happened to this kid? And then after 6 seconds, he's finally starting to fall, right? He's starting to have a negative velocity starting to go down, right? All right. What a weird equation for a kid falling off a cliff. Anyways, last but not least now is this guy right here is to calculate the acceleration, right? Calculate the acceleration. And to calculate the acceleration, I'm just going to tell you right now, if the velocity is the rate of change of the position, The acceleration is the rate of change of the velocity. How fast is the velocity changing in this problem? And in order for us to do that, that just means that I need to take the derivative of the velocity function, and that's going to tell me what the acceleration is. Okay? And this is what I want you to draw from this whole chapter, by the way. If I give you a position function, and I ask you to find the velocity exactly at a point, you need to understand, oh, take the derivative, that gives you the velocity. If I give you the position function and I ask you to find the acceleration of something at a specific time, that means to take the derivative not once, that gives you the velocity, take the derivative of the velocity function, and that will give you your acceleration. That's the connection between all of these guys. And that's why physics and calculus is so connected with each other. It's simply just because you take the derivative of position, you get velocity. Take the derivative of velocity, and you get acceleration. Okay? And that's that. I have one more example. I don't know if we have enough time for it, but it's something that you guys should try to do. Oh, I should finish off this problem, shouldn't I? The derivative of velocity then, right? The derivative of velocity is going to equal to the derivative of 135 is just 0. The derivative of negative 32t is just going to be negative 32, which means the acceleration, right, is equal to negative 32. The acceleration is a constant, isn't it? And hopefully that makes sense, right? As this guy's traveling up, gravity, the acceleration due to gravity is consistently pulling this guy down, so he's just not going to fly off forever. He's going to reach a peak, and then he's going to start falling down towards the Earth. And as he's falling down, the acceleration is still negative, and he's going to start falling faster and faster. The velocity is going to get more and more negative. Okay? There is one more example, but I don't think we're going to have time for it. But I just want to show you this right here. Let's go back to the example with the rock that we're looking at right here, right? With this rock, not the rock, but this rock. Right? Hopefully you guys can see this okay. I hope you guys can see that okay. So that red line, right, is the slope of the tangent line, right, or the derivative evaluated at each of these values along right here. And I hope you guys can see, if I were to graph that derivative, if I was to graph the derivative, f prime of x, if I were to graph it, it's this purple line right here. And I hope that makes sense why it's that purple line right there. Because check this out. When I'm over here, right, when I'm over here at x equals to 0, the tangent line is this red line right here, right? It has a very positive slope. But as I move along there, the positive slope gets less and less steep, right? So this purple line gets decreasing right here. The value of that velocity is decreasing because the slope of that tangent line is decreasing, right? Let me go ahead and graph this dot here. Let's go with a comma f prime of a. So check this out. So check this out, check this out. Right here, see that black dot right there? It's at this value. That's because the slope of that tangent line is 160. And as I move it along here, it's getting less and less steep. So the value of the derivative right here is going down further and further right there until it reaches the peak, where then it has a velocity of 0, and then it has a velocity that's negative because after that, this thing starts to fall, right? So it has more and more of a negative velocity because it's going now back towards the Earth. Anyways, I didn't have enough time for that second example, so you guys will stop here. Your homework will be posted. It's already on Canvas. I just haven't put the link to it yet, but you should look for it right there. There will be practice for the velocity and acceleration and position problems on there, along with some practice with derivatives using trig functions again. So be ready for that. And that's it for me, guys. Have a good weekend, right? Get started on this homework and be ready for a quiz on Monday, okay? All right, guys. Have a good weekend, guys. I'll see you guys later. Stay out of trouble. Stay out of jail. Don't get pregnant, all right? Bye, guys.
Mr. Knockney, I have a quick question on how to do